I'm going to talk about hash-based signatures. My name is John Kelsey. I work at NIST, and I'm also coming here and doing an industrial PhD with Bart. And so I come show up here for a week or two at a time every now and then otherwise I'm in Maryland working on standards or trying to do research and trying to debate people, trying to get me to come to meetings. So, big picture of this is I'm going to talk about kind of the basics of hash-based signatures, how they work, kind of what the ideas are behind them. And so I'm going to talk about one-time signatures and few-time signatures and Merkle trees and hypertrees, and then how you put these together into full schemes that are practical. We do stateful and stateless hash-based signatures. And one thing I'm going to say, I'm only talking about the kind of the standard, like the classic hash-based signatures, so stuff where you're basically doing things in a Merkle tree. I'm not talking about Picnic. Picnic is also, you can think of it as a hash-based signature. It's actually kind of an encryption. It's a symmetric crypto-based signature scheme, but it uses MPC in the head and it's completely unrelated, so I'm not going to talk about it at all. So my goal is that at the end of this, you'll know how hash-based signatures work and you'll be able to follow along in a presentation and read a paper and get what's going on. You'll even be able to read some of these specs. I have to warn you though, some of the specs on these things, even though the ideas are simple, are fairly thick. And hopefully also there are a lot of kind of tools for your toolkit that are used in these hash-based signatures that you probably should know because they're useful for other things. Okay. In particular, Merkle trees. I mean, probably you all know what Merkle trees are, but if you don't, you should know them because they're like amazing, useful tools. So to start out, hash-based signatures are actually really simple. All of the underlying ideas are simple. All right. Basically, they are generally based on one-time signature schemes or sometimes few-time signature schemes, which means you can sign once and it's secure, but if you sign a second time, you lose your security. Or sometimes maybe you can sign 5 times, but the 6th time you lose your security. And so that means that making them practical gets really ugly. Okay? So the sort of the story of hash-based signatures is you're going to start with a really simple set of ideas, and then another simple set of ideas, and then another simple set of ideas, and then some optimizations and some tweaks and some tricks. And by the end, you've got this really complicated scheme that's a little intimidating to look at at first. So if you look at XMSS or you look at Sphinx Plus, they're fairly complicated schemes, right? And it's really weird because the underlying ideas are really simple, right? There's nothing in these underlying ideas that is hard to get. It's just that you have to pile on the optimizations to get something that's just barely workable. So that's the story of hash-based signatures in a nutshell. So what I'm going to do is I'm going to start with one-time signatures, and eventually I'll talk about few-time signatures a little later. And then I'm going to talk about how to use Merkle trees to combine them into like a lot of one-time keys into one big composite key that you can use for signing many messages. I'm going to show you how to do hypertrees or trees of trees. And then I'm going to see how you put all of this together to get practical schemes that you can use. And these are practical schemes that people can use. You can use now. Okay? So these are sort of some principles that will apply to every hash-based signature I talk about and just all of the hash-based signatures in this kind of world. Okay? There's always a limit to how many times you can sign. Sometimes the limit is one time. Sometimes the limit for a given key is maybe 1,000,000 times, or 2 to the 50 times, or 2 to the 64 times. There's always a limit. And the reason there's always a limit is that signing is releasing some secret data, right? When you sign something, you're releasing some secrets. And so unless you have like some unbounded signature length, you're always, an unbounded key size, you're always going to have a limit where you've revealed too much secret data, and now the attacker can start forging messages. And verifying is almost always just going to be, you take some output from a signature and you hash it somehow and check it against a public key. And these underlying ideas are simple, even though the full schemes get a little complicated. So I don't think I have to explain what a hash function is, but I did prepare the slides, so I'll tell you. Basically, a hash function is just a function that lets you compute over a big message and get like a nice digest, and then you can use that as a stand-in for the message. The reason to have a hash function originally, the reason they were invented, is so you could sign messages. You know, if you're trying to do an RSA signature or something, well, you can't fit a 1,000,000-bit message into an RSA modulus. So you want something that will fit. And so there are 3 properties we always talk about when we talk about hash functions. And this is pretty basic, but I'll just go ahead and cover them. First thing is collision resistance. That just means it should be hard for you to find two messages and give them to me that where these two messages have the same hash output. Okay. So this is sort of weird because if you think about it, you might be hashing a 1,000,000-bit message and getting a 256-bit output. So just by counting, you can see that there are a huge number of collisions. Okay. But the idea is it's supposed to be hard to find them. And when you try to define this property theoretically, it gets, to my mind, a little ugly, a little messy. But it's sort of, the general idea is nobody should be able to show you a pair of messages that collide. And if they do, then they've broken the hash function. You throw the hash function away. It's interesting. This is a very strong property of a hash function. This is a very strong thing. This is a very demanding thing to expect of a function, okay? Because the function's public. You as an attacker know everything going on inside that function. You're trying to make collisions happen. And we've actually seen that widely used hash functions as of a few years ago, like MD4, MD5, SHA-0, and SHA-1, all got broken. And they got broken by attacks where the attacker basically just looks at the inside of the function and can decide things like, my differential characteristic didn't go through. I think I'll just change this message bit and make it work, right? So this is a very strong property. You'd like to require less of your function. You'd like to be less demanding on the security of your function. And so that's where we get to these other properties. Second preimage resistance. So for a collision, I have to find two messages that have the same hash. For a second preimage, it's a little harder. I'm going to choose a message, and then you've got to find another message with the same hash as my first message. So you can think of it, if you use the fingerprint analogy, you can think of collisions as I'm trying to find two people in the world with the same fingerprints. And the second problem is I've got a suspect and I want to find somebody else with the same fingerprint so I can frame the other guy for the murder or something. So this is inherently feels like a harder problem, and it is. So all those hash functions we've broken, MD4, MD5, SHA-0, SHA-1, we can find collisions for them. For MD4 and MD5, we can find collisions you could probably write some app for your phone to find them. They're really fast. Okay. Second preimages, nobody has any idea how to find for these, as a practical matter for any of those functions. I think even for MD4, which is a really old, really weak hash function, the best second preimage attacks are still very expensive. Nobody can do them. And it's important to note, this is a weaker property to claim on the hash function. Other thing to notice is, if you have second preimage resistance, you must have collision resistance, right? This is sort of intuitive because if you have an algorithm where I give you a message and you find a second preimage, okay, well then you can always use that to run an algorithm to find collisions, right? Choose a random message and then run the second preimage algorithm. So the other property, which seems to me to be the hardest property the most demanding property on hash, or the hardest attack, the least demanding property, is pure preimage resistance. A preimage is where I give you the target value and you find a message that hashes to it. Okay, so it's like I find a fingerprint, you got to find the person it matches. Okay, so that's really hard. Okay, now kind of theoretically, it doesn't follow. It's not clear that preimages are always harder than second preimages. There's not a reduction the way there is with preimages and collisions. But in practice, this seems like the hardest attack. So for Merkle-Damgard hashes, we know ways to do second preimage attacks that work pretty well, and they don't work at all for attacking the preimages. So I'm not going to spend my day talking about hash function properties here. I just want to say the properties that we need, for most signature schemes, we just assume collision resistance, right? You're hashing a message and then signing it with RSA. Well, now you care that somebody can't find two messages with the same hash. For most of the currently specified hash-based signature schemes that people try to make practical, they try to design them so they only need preimage resistance or preimage and second preimage resistance. And the reason for that is you can already do that with most of the mechanics of the hash-based signatures. So it makes sense to just do a little extra work and get this property even for how you hash the message. Really what that means is you generate a random prefix and stick it in front of the message before you hash it. Okay? And the important thing, the reason why anybody cares about hash-based signatures right now, where they didn't maybe so much 20 years ago, is because finding collisions and preimages and second preimages are all still hard. They're still acceptably hard with our current hash functions, even if, especially preimages and second preimages, even if you've got a quantum computer. You still can't do preimages or second preimages easily. Okay, so that's enough of the preliminary stuff. Let's jump into one-time signatures. So, all right, this is the last bit of very basic crypto 101 I'm going to talk about. What's a signature scheme? Well, it's easy to say what a signature scheme is, right? You have an algorithm that generates a key pair, public key, private key. You sign, the private key you keep secret, the public key you give to the world. When you want to sign, you run a signature algorithm with the private key and the message. It gives you a signature, and anybody can verify that signature if they know your public key, okay? And normally, you have one public key, one private key, and you sign a zillion messages with it. There's no problem. So, only reason to talk about this is we're going to be talking about a one-time signature. A one-time signature is exactly the same thing, it's a signature scheme, but with the extra property that if you sign more than one message with the same key, with the same private key, you sign two different, they have to be different messages, so signing the same message multiple times doesn't hurt anything. But if you sign two different messages with the same key, then you lose all your security. And then there are also these, there are algorithms called few-time signatures. So you might have a k-times signature. You might have a signature scheme that's secure until you sign 8 times. But if you sign the 8th time you sign it, you leak all your secrets. Okay. And in general, the catastrophic thing that happens is the attacker is able to forge messages from your key. So the first hash-based signature scheme is called Lamport Signatures. This actually, when I learned this, I learned it as Lamport Diffie Signatures. I think reading like Ralph Merkel's, like his PhD thesis or something. But I actually have since then seen a paper that was written by Leslie Lamport that explained these signatures. So I feel like I should assume it's just him. But anyway, sometimes you'll hear these referred to as Lamport Diffie Signatures. So how do we sign a bit? Well, this is like the simplest way you could imagine doing a signature scheme, right? So all I'm going to do is I'm going to generate 2 random values. I'm going to hash them. My public key is the hash of the 2 random values. And if I want to sign a 0, I just reveal x0. Want to sign a 1, I just reveal x1. Okay? This is, you probably could have come up with this yourself, like sitting down in a coffee shop for thinking about this for an hour. Okay? So the interesting thing here is, can I as an attacker change this signature? Well, obviously not, because to change this from a signature on a 0 to a signature on a 1, I would have to find a preimage for one of these values, for y1. I know nothing about this value until it's been given to me. I know nothing about x1, so it's a straight up preimage attack to attack this algorithm. Okay? So you can see where the security comes from, right? So this is a 1-bit signature. Signing 1-bit messages isn't all that helpful. So maybe we can, in fact, this is signing 1-bit messages once, so it's super not helpful. Let's extend this to 256 bits. And then we'll just do what every other signature algorithm does, which is we'll sign a hash, okay? So in the rest of this talk, I'm just gonna assume our hash functions are always 256 bits wide. That is, these all work with different sizes, and sometimes there are reasons to use smaller sizes because you're tuning for different attacks. I'm just gonna assume it's 256 bits because that's easy. So in this case, you're going to do Lamport. You're going to do exactly the scheme I showed you for 1-bit signatures, but you're just going to repeat it 256 times. So you're going to have a total of 512 secret values and 512 output values that are in your public key. Okay. So there's your key. There's your public key and your private key. And if you look at this, when you sign the message, all you're going to do is just choose which values to reveal. Okay? So just like before, if I want to sign, let's say I have a signature on a hash that starts 100 and then ends with a 1, I'm going to reveal, x01 for the first bit. I'm going to reveal the 0 entry for the second bit, the 0 entry for the third bit, and then the 1 entry for the last bit. I'm just going to go through the entire thing and do this. So the signature is going to be all these values outlined in blue. There are 256 random values that come out for a signature in Lamport, and they are the things that then you're going to hash back to check the signature. So verification is, again, very simple. You're just going to take the signature that I give you, and you're going to hash each of those elements and make sure they hash to the right value in the public key. So if you think about this, the public key in this scheme is 512 hashes long. The private key is 512 hashes long, and the signature is 256 hashes long. So these are fairly big. Each hash is 32 bytes in our case. So these are fairly big signatures, right? So it's kind of interesting to say, what happens if we reuse a key? So these are one-time signatures. Reusing a key is catastrophic. Why is it catastrophic? Well, here I just sort of outlined what happens if you sign two different messages. So if you sign two different messages on average will have about half the bits in the hash different, okay? So what's going to happen is, in this case, you signed the same bit for bit 1, or for the first bit and the second bit, okay? Which means you are no worse off now than you were, right? After just one signature. We didn't reveal anything extra to the attacker. But for these other two bits, we've revealed both the 0 and the 1 preimage for both of these. And what that means is that for about half of the bits, the attacker is now going to have a free choice. When he wants to forge a signature, he'll be able to say, I can forge a signature that matches on the matching bits, right? But it can be anything on those bits where I have both choices. And so just describing the same idea. And one of the interesting things here is, if you sign 3 or 4 times, it just gets easier and easier. So it's getting exponentially easier. So after 2 signatures, half the bits are free. After 3 signatures, like 3/4 of the bits are free. After 4 signatures, 7/8 of the bits are free. Because every time, about half of the bits will be different in the next message, relative to what you've already seen. So you can kind of see that you get this pattern where some of the bits are free, some of the bits are fixed, and now you're going to try to find a message that matches to the fixed bits and takes on whatever value it wants to take on in the free bits. And that's how you're going to forge. So this is a really simple scheme, right? Generating a key is just generating some random numbers. That's actually really common. That's all of these schemes. The way you start generating keys is you generate random numbers, and then you hash them. Signing is releasing half your secrets. Okay, half your random values you're releasing. So right off the top, you can see intuitively why can't you sign more than once with this scheme? Well, every time I sign, I reveal half my private key. So it's sort of intuitive that, gosh, I can't do that very often before I've lost all my security. Verifying is just hashing the values from the signature and matching them to the public key. And all of this pattern occurs in these more complicated schemes I'm going to talk about. So, do I have any questions about Lamport signatures? Everything makes sense? Okay, this is a really simple scheme. Like I said, this is the sort of thing I feel like if I told you, think about how to make a one-time signature scheme from a hash function, and you had an hour with a cup of coffee and a notebook, you'd probably come up with something like this without any trouble, right? It's, but it's kind of cool that you actually can make something that looks like a signature scheme out of just hash functions, right? So now let's talk about a better scheme. This is called winner nits, and it's based on hash chains. So the trick is, it's a slightly later one-time signature scheme based on hash functions, and it allows you to have much shorter signatures and make a trade-off between signature length and work. Okay. So to talk about this, we need to talk about a hash chain. Now, I'll just say up front, sometimes when people say hash chain, they mean something like a blockchain where you're putting additional information in each time. In this context, what we mean by a hash chain is it's just a way of computing sort of a pseudo-random sequence. So we're starting with an input value and we're hashing it repeatedly until we get to the endpoint. And I showed you this with the hashes and then with the lines because I want to be clear that in the rest of this talk, I'm going to use this lower notation with just the arrows, where each arrow represents a hash operation and each node represents a value. And the reason for that is because it's just more compact and easier to write. So a couple things you need to realize. If I give you any value in this hash chain, you can always go forward, right? If I give you any value in this hash chain, you can't go backward, right? Because to go backward is to find a preimage to the hash function. So once again, you see this preimage resistance coming up as an actual property in what we're going to be talking about. So here's a sort of a trick for signing 2 bits at a time with one hash chain. So before we needed 2 hashes to sign 1 bit. Now we're going to have 1 hash to sign 2 bits. Okay? So I've got a hash chain of like 4. And in order to sign a 2-bit value, I'm just going to take the 2-bit value, represented as an integer. So it's going to be an integer between 0 and 3. And I'm going to use that to say how many times I need to step forward from my initial value. So in this case, I'm signing a 1. So I'm going to step forward 1 time. I'm going to compute the hash 1 time. That'll be my signature. And then when you want to verify, you're just going to take that value and step forward 3 times with the hash function, hash, hash, hash. And that will let you verify that it's the right value. So this will work with a chain of length 2 to the w for any w. And so we can just extend this once again to the whole hash. In this case, each chain has 2 to the power w. So let's say maybe it's 2 to the 4. So we've got 16 elements in each chain. And then we're going to encode 4 bits on each chain, exactly the way I showed you. And so this looks pretty good. And it almost works. Almost. There is, however, an attack. So anybody who doesn't know, I'm like, okay, yeah, you know the attack, right? Anybody who doesn't know the attack, and you see what's wrong with this as a signature. What bad thing can I do when somebody gives me a signature with this? It might be easier to go to this page, to this picture to look. So I've got a signature for 1. Can I change it into a signature for something else? Yeah, you just hash it again, right? So this hash chain keeps you from going backward, doesn't keep you from going forward. So if you want to assign a 2-bit value, you've assigned a 1, but I can change it to a signature on a 2 or 3. Hello? So that's my proof of P equals NP. So I won't be talking about this again. Thanks. Okay. So this scheme almost works, but we need an extra tweak. And you can think about it, again, if you don't know how these schemes work, you can think for a minute, well, what would I do to make this not work? I often find that it's fun to try to solve the problem myself before I see how people solved it, just because then I'll understand why they did what they did. So a natural thing you might think of here is run the hash chains forward and backwards and assign each W-bit chunk twice. I think that may be like in the original paper or something, one of the things that people thought about early on, but there's a much nicer solution, okay? And so the problem here is just that the attacker can increment the values. So we somehow need a way of keeping the attacker from being able to increment values to change the hash, or to change the signature. So I'm going to use a physical analogy for this. And this is cool because this is one of those things where you can actually use this. This actually would work, right? You have indelible, so let's suppose I have like a magic marker, indelible ink marker, and I want to make a mark using tallies. I'm going to write some numbers. And I want it to be impossible for anybody to change the number once I've written it without it being obvious that they've changed it. So I want to check something that nobody can change. But what I want to do is I'm using an indelible marker, so nobody can erase the marks, but of course other people have magic markers, so they could add things, right? So anybody can trivially just bring their own marker and add one of these marks to the tally mark and change my number. So if I don't want that, what could I do to stop that? Anybody got any ideas? Like probably 3/4 of you already know how these work, but okay. So here's a trick for stopping it. Let's assume that each of these tally marks we're only going to allow a maximum of 5, to be a maximum of 5. So we're going to say the biggest number of the sum of all these that it could possibly be is 15. So we're going to define a checksum as that maximum number minus the actual sum. Okay? And the whole point is now when you add 1 to any of these numbers down here, you have to subtract 1 from these. But of course you can't erase indelible ink markers. So you can't erase them. You can't go down, okay, yeah, you could probably figure out a way to erase them, but go with the model. So if I want to add something here, I would have to delete the checksum. Also, another thing I might want to do is I might want to add something to one of these and subtract it to the other to keep the checksum unchanged. But once again, that would require erasing one of my marks. Okay? So with this checksum, we ensure that an attacker has to make some number go down. Okay? And this actually would work. I mean, if you want to make a thing with a magic marker on a piece of paper or something, really nobody will, unless they can actually erase the indelible ink or replace the paper, they really won't be able to change the number. So obviously this is, we don't care so much about making marks with magic markers. We do care about finding a solution to our problem with winter nits. So what we're going to do winter nits with the checksum is we're going to break the hash into these W-bit chunks, just like before. We're going to then compute what the maximum value is based on the number of components, okay? The number of pieces we need. So for example, if we're doing 4-bit chunks and we've got it to a 56-bit hash, then we're going to have 64 of those. So we're going to figure out, 15 times 64. That's going to be our max. And then we're going to compute this checksum that's the maximum minus the actual sum, just like we did before with the tally marks. And the idea is now the attacker can increase any of those digits that he wants, but he can't fix the checksum. The checksum will always be wrong unless he, if he changes anything, the checksum will always be wrong because he can only make numbers bigger. He can never make them smaller. So we encode this, you have to think about for a minute, okay, one simple way you could do this is you could encode the checksum as a huge long chain that was way longer than all the others. That'd be a little unwieldy. So in practice, you're going to break that into chains of the same length that you're using for the rest of the signature. And so if we've got 16 long hash chains, we're encoding 4 bits apiece, then you can get the calculation and figure out we're going to need this many bits, log of 960 bits, which is a little less than 10 bits. And so we're going to use 3 chains, each with 4 bits. And so now we're going to be able to represent the whole signature with 67 hashes in this case. Okay. So you can look at this and say, well, could an attacker decrease this checksum? Really what we're doing when we write the checksum down, and we encode it in these hash chains, what we're doing is we're writing it in a base 2 to the W form, right? So we're writing it where the first digit is the first number of steps is the first digit base 2 to the W, base 16, and the second is the second digit, base 2 to the 16, or base 16. And, pardon me. And so you're writing this, and so the only way you can make this smaller is to make one of the digits go down, right? In this context, you can't do rollover, you can't do overflows. So the only thing, so if you can only increase the digits, right? Imagine a counter that's like decimal digits, right? 345 or something. You can never make a smaller number without making at least one of those digits get smaller, right? So you construct the key. You've got some choices. This W parameter lets you choose quite a wide range of trade-offs between the work done to set up to generate these keys and sign and verify, and the size of the signatures. And so you can see you see the kind of the trade-off. I've got a better table here a little later on, but let me show you. Let's kind of walk through how this all works. So for making a winner NIST public key, we've got the first, in this case, the first 64 chains that are going to be used for the hash, and then the last 3 that are going to be used for the checksum. And the way we're going to do this is, we're going to send, although this is the amount of work we're going to do to compute this. So basically, for each chain, you're going to have to do 16 hashes, and then you've got to do that for all the chains. So you just sum them up. And the nice thing about this, and I'll explain why in a second, when we're using this, the verifier doesn't need this whole Y0 through Y66 public key. All the verifier needs is the hash, because during the verifying process, you reconstruct the private or the public key. So when assigned with winner NIST, the first step is we take the hash, we take the message, hash it, break it into 4-bit chunks, and compute our checksum. And then we get a base, in this case, a base 16 number, right? And then for each of those components, each of these digits in this base 16 number, that's going to tell us how many times to step forward in the hash chain. So we get a 0, we step forward 0 times. We just reveal this value. If we get a 2, we step forward 2 times, and then we reveal what we find there. So we take x10 and we hash. And for the second chunk of 16 bits, we're going to step 7 times, and so on, right? And so our signature is just this sequence of red outlined values. So in this case, our signature is going to be 67 values that are all pieces in this hash chain. Does that make sense? Right. And so then verifying works just the same way at first, right? We're going to do the same thing where we write the number, hash it, compute the checksum, write it as a base 16 number. And now the only difference here is we don't start with a private key, we start with the signature. And we have to take our value and do a little computation and say how much of the chain was left. So if there were 16 steps and the highest number you could have encoded is 15, the lowest is a 0. If you encoded a 0, then I should need to step 15 times. If I encoded a 1, you should need to step 14 times, and so on. And so you can figure out from here, pretty straightforward way, how to verify. And the interesting thing is, when you're done verifying, you start with a signature, and you verify, and you get this sort of thing that is a candidate public key. You don't know yet that it's the correct public key. But if the signature was valid, then this is the correct public key. Okay? And so then the last step is, if I've sent you the signature and the public key that I've sent you is actually the hash of the correct values of y, then you can take this public key, this sort of candidate public key you've reconstructed, hash it and check it against my actual public key, and say, okay, this is good, this is a match. And this is quite nice, because if you're using Lamport signatures, the public key is 512 hashes. And there's not a nice way to just send the hash of those or something, so you have to send the whole big blob. So this becomes a lot more practical. So this is a table that shows more or less how you trade off work for signature size. I'm making a bunch of assumptions here, so like all my hashes are 32 bytes. I'm not doing any optimizations, and also I'm not including like prefixes and stuff. So when you look at fully specified schemes, the numbers will be a little different from this, but this is pretty close. Okay, so if you choose W, each choice of W gives you a different trade-off between signatures and how much work you do for key generation. And in general, signing and verifying each cost about half the work of key generation. Okay, so the interesting thing to notice here is down here in this top part, which is the place where most people are, when they implement these things, they live. These are, you can see where you're getting a pretty big advantage in terms of savings of size. And at the same time, you're still doing a pretty reasonable amount of work. You can go much further down. You can go to the 12, to the 16, all the way to, I calculated out to the 32. So each chain is 4 billion steps long. In that case, you've got a 320 byte signature, which is quite small. That looks really good, but it costs you, it's 2 to the 35 hash operations to compute. So, doing this one-time signature might take you a little while. I mean, probably still under a second on a good machine, or 2 or 3 seconds, but still, it's pretty substantial. And the work here matters because later on we're going to be generating large sets of these keys, and then having each one take a second means that you can't generate a big key. And other thing to note here is you compare it with Lamport signatures, and you can see that WinterNIST signatures dominate Lamport signatures in every way. They're better, they're faster, they're shorter. The only thing not to like about them is they're a little more complicated to explain, but not all that much more, right? I mean, I think, coding this up is not hard, right? None of this is very complicated. So, if I tell you, go code up from scratch, elliptic curve, ECDSA, okay, that sounds like a lot of work. If I tell you, go code this up from scratch, you can probably do it. As long as you have a hash implementation, you can do it really quickly. Of course, I guess if you have the right big num package, you could do the number theoretic stuff too. So a few messy details, because here in this talk, I'm mostly not talking about the messy details, but I do want to point them out. So when you actually fully specify these schemes, you probably want to make them based on second preimage resistance and preimage resistance rather than collision resistance. More or less what that means is you generate a random prefix that gets hashed in before you hash the message. Sometimes you also might generate a random mask that gets XORed in before and after. That's XMSS does this. Okay, and the idea is that now even if you can find collisions in the hash function, you can't do anything with the hash. If you as an attacker, if you're not the signer, so let's say that you're submitting things to me to sign, even if you have an algorithm to find collisions on the hash function, if I stick a random prefix before the message, before I hash it, then almost certainly that just breaks your collision algorithm. So another detail that matters is multi-target attacks. That matters for WinterNIST. It matters even more when we start talking about the Merkle trees and stuff. And so the idea is when we're doing a lot of these attacks wind up being preimage attacks, right? I say in order to break this, you have to find a message that hashes to a particular value. But if you look at a WinterNIST signature, well, now I'm giving you maybe 34 of these values, or maybe I'm giving you 67 of these values. There are 67 targets. So that means it's going to be more or less 67 times as easy, okay? And when we build a huge tree with millions of these things, and there are going to be a lot of places you could try generating random values and hashing them and seeing if you can get them to land someplace. And that's a nice way of attacking this kind of system. And so the solution is you basically make each hash computation unique. You sort of domain separate things. And that way, when you do a brute force search, try to match one place, it can only go to that place because you had to choose an input that was unique. Last thing is storage requirements. So if you look at this, the private keys look really big, but actually you never would store the private keys for these things normally, right? You might generate the whole private key just to make the coding easy when you're signing something, but you wouldn't keep it around. Instead, you're going to have a PRF, right? Something like HMAC, okay? And then you're going to choose that PRF key, and then from there you're going to have some sort of unique identifier for each key that you use, and for each key you're going to hash together a bunch of stuff and index and generate the secret value. So the result of that is you don't have to have a lot of storage. I'll talk in a minute about how someplace where we do still run into problems with storage. But first of all, are there any questions about Lamport signatures? Okay, so this is all pretty easy, right? None of this is, it's sort of interesting because all these concepts are easy. It's just that when you build them up, you wind up with fairly complicated schemes at the end. So, let me get a drink here. Next thing to talk about is Merkle trees and how to basically make a tree of keys. And so the whole point here is we're going to figure out how to make these one-time signature schemes useful. Okay, so what does useful mean? Useful means, more or less, it's not useful if I have a public key scheme, like a signature scheme that only lets me sign once. Okay, that's a toy. If I could sign hundreds of times, maybe it would be useful in some niche application. Thousands of times, really I want to be able to sign a whole lot of times, maybe millions. And depending on exactly your application, it may be you can say, I only need, I'm doing firmware updates for a particular piece of hardware and I will never do more than 100 of those in my lifetime. And then you could have a fairly small scheme that only could do 100 signatures, right? But you need this number of signatures to be bigger in order for this to be useful. And also you need to have signatures that are not too big and not too slow to compute. So that's what we mean by useful. And so there's this obvious strategy, which is we're just going to combine a whole lot of one-time keys into a single sort of composite public key. And you can even imagine doing this as a list. So I have a million WinterNIT's public keys. I'm just going to stick them in a big list and send them around. It's just a 32 megabyte public key, right? And I mean, okay, some of the post-quantum algorithms do have very big public keys, but that wouldn't be very efficient, right? So we're going to use Merkle trees. And if you know what a Merkle tree is, that's the absolutely obvious tool to use for this job. So you see this thing and the first thing you think is, yeah, you'd use a Merkle tree for this, right? So how many of you know what a Merkle tree is? Okay, not everybody, but most of you. Okay, well, the ones who don't, this is a good day for you because Merkle trees are super useful. They get used in all of crypto, so that's assuming you're not just like asleep or something. So a Merkle tree is just a binary tree you're going to make by hashing things together. Okay, and so a nice way of thinking about this, we're going to start with a list. That's nice if it's a list that's a power of 2 long. And we're just going to hash pairs together. So we're just going to take pairs, concatenate them, and hash them. Okay. And then we're just going to take, now we've gone from 16 values to 8 values. So we're just going to iterate. We'll just do the same thing again, and again, and again, until we get to a root. And so you can convince yourself this root, because it's been computed with a hash function that ultimately goes back to all of these leaves, this root sort of incorporates information about every one of these leaves. Okay. If I were to change this leaf value, okay, then this root would have to change because otherwise, if I change this, but this doesn't change, that's a collision on the hash function, right? Or if this one changes, but this one doesn't. Somewhere there would have to be a collision in the hash function if I could make a change and not have this, not have it propagate all the way to the root. So that's a sort of an intuition for why this should be good. So the nice thing about a Merkle tree is you can efficiently prove membership in a list, okay, and actually position as well. So the kind of big idea of what I'm going to do, I want to prove to you PK4. I want to prove that it's in my list, and I want to prove where it is in my list. So what I'm going to do is I'm going to help you recompute these hash values so you can recompute the root. You're going to recompute the root, including my value that I'm trying to prove to you. And that will be enough to convince you that I must be telling you the truth about what was in this position in the tree originally. So I need to be able to help you compute all of these hash computations. And the interesting thing is, I don't have to tell you the whole tree. I don't have to give you all the leaves and have you recompute it. I just have to give you a few values. So these red values are the ones I'm going to reveal to you. And so you can see, okay, PK5 is another leaf. I need that to get that first hash value. And then I'm going to tell you this hash value. You don't have to verify it. Because if I lie to you, then I will, if I make this up and it's the wrong value, then all the rest of these values should be wrong. Right? Because otherwise I've got a collision for the hash function. And so you can kind of go down this list and see if I give you those values, we've got a root, we've got a Merkle tree root. And you can recompute it, and once you've recomputed it, then you can convince yourself that that public key that I've got circled there is in fact in my list of public keys. Okay? And even more than that, it's not just that you know that it's in the list, you know where it is in the list. And for one of the schemes I'll talk about later, that matters. So this is a Merkle, so this is basically Merkle trees. Merkle trees are incredibly useful. They get used all over the place in crypto. If you've played around with blockchain at all, they're there. Digital timestamping, which is sort of the prior, kind of the prior implementation of that idea without the distributed consensus, uses blockchains. Certificate transparency uses them. Redactable signatures, if you've ever seen those. But I mean, you could write like 100 things, right? These are super useful tools that get used everywhere. So, do you have any questions about the Merkle trees? Yeah, I think I'm going over stuff you already know. That's fine. So, now that we've built up some tools, I want to talk about how to build simple stateful hash-based signatures. This is where you get to something you can actually use. And I want to point out, we should have like one of those disco balls hanging from the top here, because we're still in 1979, okay? We're basically, all of this is stuff you could have found out by hanging around the EE in math department at Stanford in the late 70s. Ralph Merkle and Marty Hellman and Whit Diffie are chatting, right? And so all this stuff goes back, and Lamport and Winternitz, I think, are there. So all this stuff goes back to the late 70s. So I'm sorry I didn't have like a leisure suit or something, or like a polyester, but. So the big idea for this hash-based signature, there's a wonderful quote by Paul Graham, who's a startup guy, a Y Combinator guy, that said that a surprising number of problems, the best solution to the problem starts with the phrase, yeah, but what if we just, right? So what if I just did the obvious thing and just brute forced it? Well, a lot of hash-based signatures, the answer to the question is, well, but what if I just did the obvious thing? So what I'm going to do here, I've built a Merkle tree with a big list of keys in it. I'm going to make a big list of these, 2 to the H of these one-time signing keys, okay? I'm going to put them all in a Merkle tree. My public key, my kind of composite public key, the one I'm going to use, that I'm going to give everybody, is going to be the root of this Merkle tree. And every signature is just going to be a Merkle tree path plus a one-time signature from the leaf. So for key generation, this gets kind of interesting. If I want 1,000,000 one-time keys, I want to be able to sign 1,000,000 times, right? And I'm using Winternitz with W = 4. Each Winternitz key is going to take around 2 to the 10, so around 1,000 hashes to construct. Which means that to get 1,000,000 keys, I'm going to need to do about 1 billion hashes, okay? Now that's fine, 1 billion hashes is not too bad on a modern machine. But you can see that there's going to be a limit here. If I wanted 2 to the 40 of these keys, it'd start getting to where I couldn't do this computation. It would take too long to make my public key. Okay. So this is basically the picture of how signing works with this scheme. And it's exactly what you'd expect. So what you're going to do is when you want to sign something, you're going to choose one of the keys, one of the leaves. So one of the public keys in your list. You're going to produce a Merkle tree path that proves that that is in your big public key. And then you're going to release the public key, the hash of it, right? The hash of this Y value from the Winternitz signature. And then you're going to produce the Winternitz signature itself. And that's your final signature. That's your signature on your message. So the tricky thing, actually the hardest engineering part of this is choosing the signing key, making sure it's unused. And I'll talk a little bit about that later. That's potentially kind of bad. They're kind of hard to do. So verifying signatures, once again, it's just the most obvious thing in the world. Verify the tree path. Once you've verified the tree path, you believe this one-time key is legit, and then you verify the signature with the one-time key. So everything is just follows directly from what you'd expect. So what do we call these stateful signatures? Well, remember, if I ever reuse a key, bad things are going to happen, right? Once I've used the same key twice, you can probably forge signatures, okay? And so at that point, if we kind of look at it, when we were talking about one-time signatures, maybe this was just a toy example, so it didn't seem such a problem. Here I've got maybe 1 million keys in my tree, and everybody accepts signatures from me by verifying the tree path and then verifying the signature from the, so they verify the tree path for the one-time key I'm using and then verify the signature for the one-time key. Nowhere in there are they looking up whether or not I've used this key before, okay? So the problem is, with this kind of a scheme, maybe I have 1 million keys in my thing. Maybe I've got like a device, like a laptop, and I've got 1 million keys stored on there. And somehow I screw up and I use the same key to sign 2 different messages. And at that point, you learn enough to forge messages from me. And now you can forge a huge number of, not just one message, but as many as you want, because no signer is going to check, right? I mean, it's not their problem. They're trying to behave just like with current widely used signature schemes. I run a verify algorithm and then I'm done. In fact, if you think about it, over like 30 years plus of trying, we've gotten almost nobody to check CRLs when they're using public keys. So nobody wants to do anything where they check an online server before they accept a public key. You could sort of imagine trying to do a CRL-like thing for like hash-based signatures, but it'd be a little weird. And so the reason why we call this stateful is because I, as a signer, have to keep track of the state. I have to keep track of where I am in the tree, okay? So basically it just means I need a counter that always goes up every time I sign and never can go down or stay the same, okay? So that doesn't sound like it should be engineering, like an engineering impossibility. It's actually harder than it looks. So one of the problems is you could have, a device that just fails at the wrong time. A lot of the way computer storage works, you write something to disk and it hasn't really been written to long-term memory right when you write it. It might be a little while because it's in one of many layers of cache. Okay, and it's often quite hard to figure out what's going on with actually storing things. You also have things like programs that are running in virtual machines in the cloud, and you can clone VMs. And so now, actually cloned VMs are a nightmare for basically all crypto, but this is one particular place where it's really bad because now suddenly we have 2 instances of me, each with the same state and each signing using the same keys. Also could have like hardware failures, maybe something where I can kind of glitch the clock of the smart card to get it not to write not to increment a counter, not to write a new value to storage, and then the smart card gives me 2 signatures on the same key, and then from then on I can be the smart card, I can sign everything with it, right? So there's a lot of potential for this to go wrong. Sorry. So this is the term that was, I forget who it was, somebody from Google that came up with the term of a foot cannon. So, okay, so if you watched Westerns in your childhood, which you probably didn't because you didn't grow up when I did in the US, but Westerns were, you always would have a cowboy with a gun, and so the incompetent cowboy, the idea is he reaches for his gun and he pulls the trigger and shoots his foot, right? So you shooting yourself in the foot is a common expression for screwing up by incompetence. And in this case, instead of just a gun, it's a cannon. So you're just going to blow your whole foot off, right? You're not just going to nail your big toe. And so we really want to think about how to avoid the foot cannon. So there are a lot of ways. We're actually, at NIST, we're working on, I'm not in that group, but I keep getting pulled in to discussions with them. We're working on what we can standardize for stateful hash-based signatures. And this comes up. And we've talked a lot about what can we do to prevent kind of this disaster where you reuse a key. And some ideas we've talked about, things like saying, well, these can only be used, at least for FIPS validated stuff, they can only be used if they're implemented in hardware, so they can't somehow find their way into some cloud environment and they're being cloned. Maybe there be no way to get a signing key out of the HSM. That has other problems because then you can't back up. We have a lot of ideas for what we might be able to do. But generally, I think this is an open issue, and it's an open issue that is both an interesting crypto problem and an interesting engineering problem, and it's all of the spectrum between those. So there are solutions that are actually crypto, and I'm going to talk about one of them. And then there are also solutions that are just pure engineering, like, okay, I'm going to design my memory so that there's a sort of a fail-safe. You know, if I push this button and say write, it'll always get to the disk or something. So other things that can be practical issues with these schemes, signatures are long. Actually, one of the things that's interesting is you think about this Merkle tree. Let me go back to a picture of a Merkle tree. There. Think about this Merkle tree. When I need to compute a path, I'll even go back a couple more pictures. I need to compute a path on this. I need to know a lot of these intermediate values. Okay? So if I can store all these leaves in memory and I can store all the nodes in memory, no problem. I can do this very quickly. If I'm only generating each leaf node when I need it using a PRF, then I have this interesting problem that I have to know a whole bunch of these values, intermediate values in the tree, which I don't necessarily have handy. And so this turns into sort of an interesting engineering problem. And so there are clever algorithms for trying to minimize this, where you keep track of, you cache values from previous signatures, and then you have to think ahead a few signatures and do a little extra computation, because sometimes you're going to roll over and you need to compute a value that you don't have that's going to require a lot of work. Okay, and this isn't a big issue for this discussion, but it's kind of useful to point out, figuring out how to do this. Figuring out how to do this in small memory requires some cleverness, and it actually would be easier if you could store the whole Merkle tree in memory. But if you've got 1 million signatures, you've got something like, it's going to be like 64 meg to store all this tree in memory or something, and that's a lot. So there are other messy details we mostly don't need to worry about, but the full schemes do include things for basing things on second preimage attacks. Oh, and I guess I should say, you could use different hash functions or different output sizes for the different components. So you might use a different hash function for the Merkle tree that's optimized for taking only 2 hash outputs and producing 1. These are implementation details. And so there are 2 existing stateful hash-based signature schemes. So these are going through IETF for standardization. And they're XMSS and LMS. If you look at them, they're really similar. They look like twins, or they look like, at least like brothers. Okay. LMS is a little simpler, a little more efficient. It makes slightly more demands on the hash function, right, in terms of the security proofs. XMSS makes fewer demands on the hash function, but it's a little more complicated. You have to generate pseudorandom masks and XOR min. Both of them are based on WinterNIT's one-time signatures and Merkle trees. So just the stuff we've talked about. So both of these are things you could build from what you knew in 1979, 1980. Okay, and both of them have this whole property that they're stateful. So you have to, it's the signer's job to not reuse a key, and if he screws up, he screws up. NIST is working on plans to standardize maybe a subset of these 2 schemes. And this is a place where this is giving us a lot of heartburn because of the whole misuse ability. So this is what the performance looks like in terms of size. Actually, in terms of speed, these things are quite fast. If you have really large trees, sometimes the key generation is a little slow, but the actual signing and verifying is very fast for these. Okay. So you can see these are kind of very similar sizes, very similar. One thing that's a little tricky is LMS signatures are defined for W equals 1, 2, 4, and 8. Whereas XMSS only defined for 1, 2, and 4. So you kind of have to notice that when looking at the table. But if you look, all of these are within maybe 50 or 60 bytes of each other, right? So the signatures are very similar, okay? And they're a little different from my numbers, where I just gave a quick summary of the numbers, because they include like the prefix and they include some extra bits. But these are broadly similar schemes. And so you can say, if you need to do this is kind of an interesting thing. If you feel like you can manage the state properly, these are things you could use, and you can use them today, and you get post-quantum security on signatures. They're stateful hash-based signatures. There's a lot. You have to worry about the state, but if you can do the state, if you can manage the state correctly, then you've got a good scheme. So, anybody have questions on stateful hash-based signatures? No. This is an audience with few questions. So, this might be something that is new to more of you. These are few time signatures. This is horse, fours, and fours. I love the names here. These are all based on the same idea. So I've told you how we can make a one-time signature from a hash function. It's pretty easy. I gave you two ways to do it. There's also a way that we know to make a few-time signature. Now, I should say you could make a one-time signature out of like Lamport signatures too, right? You just hash a really big hash string, right? And then it would take longer until you'd revealed enough bits to make an attacker, let an attacker forge signatures. But that's really, really inefficient, right? So this is nicer. So in this case, you're going to define a few-time signature so that you can use the same key maybe 5 times or 10 times or something. The parameters allow you to get bigger numbers, but it becomes very inefficient as you get, if you want to make a 5,000 times signature, it might be kind of a big signature or big key or something. So first I'm going to describe the initial scheme. This is called hashing onto a random subset. I'm not sure what you call it, horse, something. So anyway, the idea here is, this is basically, you can sort of think of this as an extension of Lamport, just going in a different direction than winner nets. And so we're going to do, the private key is going to be just an array of secret values, 2 to the A of them. So remember, all of these hash-based signature schemes have the same pattern. The private key is an array of random values, which is great because it means you can generate them from a PRF. The public key is basically an array of their hashes. Okay, just going to hash each one and stick it in a big array. So my public key, so maybe my private key is 2 to the 16 long, and my public key is also 2 to the 16 hashes long. Okay, so it's a very big public key. And the good news is signing and verifying is going to be really efficient. So let me show you. So key generation I just talked about is just hashing, just random number generation and hashing. Signing is a little more complicated, not too bad. Basically what you're going to do is you're going to hash your message and break it into, in this case I'm going to assume A equals 16. So we're breaking it into 16-bit chunks, just like before. And then for each of these, what we're going to do is we're going to use each of those 16-bit chunks as an index to look it up in an array. And the array is this 2 to the 16 secret values, right? So each input is just an index into an array. So if T0 is 14, then I choose the 14th entry, well, be the 15th because I'm numbered from 0, of the private key array, okay? So this one's a 0, it's going to be the first private key, first value in the private key array. If it's 65,535, it's going to be the last entry, okay? And so each time, in order to sign, we're going to take these values, we're going to look them up in the X array, and then those values are going to be our signature, okay? So once again, signing is revealing some secret data. I'm revealing part of my private key, okay? And it's sort of interesting to notice the signature is allowed to contain duplicate values. So T0 and T1 could both be 0. That'll happen a certain fraction of the time. When it does, then those two first values in the signature are the same. Okay. And this is a paper by Raisin, and it's Leonid Raisin, who's a cryptographer, and then I believe it was his dad that he wrote a paper with. So I thought that was cool. So for verification, all you're going to do is, once again, verification is hashing pieces of the signature and checking against the public key. So you're going to take this signature, you're going to hash it to get what this vector should be. And then you're going to do the same thing that I did when I signed on with the private key, you're going to do with the public key. You're going to split the hash into 16-bit chunks, use each one as an index to look it up in this array, and then construct the vector of public key elements that I should have gotten. And then you're just going to compare them, see if they're the same. Okay? So if I gave you a valid signature on this, then these two values would be the same. Okay? And so is that fairly clear? Does that make sense? Okay. Nobody's completely scratching their head. So the cool thing is you get really fast, really short signatures here, right? 16 hashes is pretty good for a signature. And actually, you can reuse this a few times without a disaster. And before we talk about why, let's just think of this intuitively, right? Lamport Signatures, every time I sign, I'm giving away half my private key. It's pretty intuitive why signing twice is going to go badly for me, right? With Untitled Signatures, it's a little more complicated because you can think of your private key as all those hash chain elements, but on average, you're giving about half your private key away, okay? When you think about this horse signature, each time you do the signature, you're giving away, in this case with 16, you're giving away 16 values out of 2 to the 16. Okay? So you're giving away a really small fraction of your private key. So just intuitively, without knowing the details of how the attacks work, you can see, kind of makes sense that you can get away with signing more than once with this scheme, right? Because you're not giving away so much of your private key. Okay. So, kind of the question of when can I forge a signature on one of these? Once somebody has signed something with horse, and I want to forge the signature. When can I forge the signature? And the answer is I need to be able to find a message where every 16-bit chunk in the hash of that message has already appeared in a previous signature. Okay? So basically, you can think of this as this private key is like a giant S box or a giant lookup table. And each time you sign, you're giving me a few elements in this. And in order to forge a signature, I need to have a message where every element of that signature I need to produce has already been revealed. Okay? So before the first signature, obviously, we're back to preimage attacks. But afterwards, we're just waiting until, we're sort of in this interesting case where the best attacks we can do are, there's a preimage attack, which we're just never going to be able to win. And then there's this thing where we have to wait around until enough values come out. Okay. Now, one thing that is kind of interesting that came out, this is GP Allison, I think, that did this, was basically pointing out that that it's really important here for you to randomize this hash. Okay. Otherwise, I, as an attacker, can go offline and try to choose a set of messages that gives me very wide coverage of all these SBox values and give me enough of these that I can forge an additional chosen message. So that attack, that's sort of an online attack is, that sort of an attack is a big deal. So it's really important to randomize these hashes. And so let's just sort of do a little bit of the math here. Suppose we've signed 4 messages already with in this case, A is the number, is like how big the tree is, so 2 to the 16, or how big the private key is, 2 to the 16. And K is how many pieces of this, how many 16-bit chunks we're using. Okay. And so after we've signed 4 times, we've already revealed as much as 64 of our secret values. Might be fewer if we had some overlap. Let's say 64 of our secret values. So we can just say that for each 16-bit component of the next message you're going to try to sign, it's, you have a probability of about 2 to the minus 10 of getting this and having, if it's just chosen randomly, of having it be one of the values that has already been revealed. Okay. And so if each chunk is 2 to the minus 10, we've got 16 of them. So for the whole hash, it would be about a 2 to the minus 60 chance. So the important thing to kind of keep in mind here is even if we randomize the hash, right? So we keep the attacker from being able to choose which intermediate chunks he gets, which particular private key values he gets. When he's trying to do a forgery after he's seen a bunch of signatures, he doesn't have to use our random number. For a forgery, he can use his own, right? He doesn't have to interact with us for the forgery. That's the whole point of the forgery. So if given what the attacker knows, he has to try something like 2 to the 160 messages before he expects to get one that he can for which he can do a forgery. That's good. That means that it's assuming that we're at a 128-bit security level. That means that we're still secure. On the other hand, you can see that if we increase the number of signatures, eventually we'll get to the point where the probability that he will be able to do this is quite high, right? Imagine we'd already revealed. Imagine that we'd already revealed 2 to the 15 of these values. Okay, then the probability would be basically like 2 to the minus 16 that a given random message would be forgeable. It'd be really easy to forge. Okay. Now, if you see, oh yes?
So to prove that this is secure, do they use random walker model or some
I believe they assume a random oracle. The specific problem that they're solving is, I'm trying to remember what the name of it was. The name of the thing is hashing onto random subsets, but it was, I think, like a set cover thing. So the thing is, if you're randomizing these hashes, then and you assume that the hash outputs are random, then basically each time you're basically doing a combinatorial problem rather than, it's more like combinatorics than cryptanalysis, if that makes any sense, right? We're looking at how many times does each of these values occur, right? So I believe that the proof is on a random oracle model, but I'd have to go look. So So there are two practical problems to solve with horse signatures. I'm trying to be careful how I pronounce this signature name. So the first thing is the public key is enormous, okay? And you don't want a huge public key for a practical scheme. The other thing is that the signature, there are weak messages. A weak message, at least if you're not randomizing the signature, a weak message is a message for which the same secret component gets used a zillion times. It's used a bunch of times. So as an example, we might just by chance have a hash of something that has the same value appear 5 times. Well, now this has got to be a lot easier to, kind of intuitively, this is easier to forge, right? Because there's only one of these components, for the first 5 of these 16-bit chunks, we're only doing one probability calculation. If it's, 2 to the minus 12 of these are, have been revealed to us, well, it's just 2 to the minus 12 for those first 5, right? We can't multiply them all together and have them be independent anymore. So those two problems, the huge public key actually means it's not usable for practical stuff, and then the reusing the same secret component means that the security analysis gets nastier. And so we'd like to fix that. And so the way we're going to fix it is by moving to one of 3 different schemes. The first scheme, which I'm actually going to talk about in some detail, was used in the original Sphinx. It's called Horst. It's just going to do, once again, we're going to do the obvious thing here, okay? And then after that, I'll talk about the other variants. So basically, the public keys are big. We've got a 2 to the 16 element public key. Now, we've just talked about exactly the thing we can do to make it very efficient to prove membership in a list. So we're just going to do that. We're just going to say, what if we put those public values into a Merkle tree, and then for each component of the signature, we would have to also provide a Merkle tree path to prove where what the value is that it's in our list. Okay, so if we did that, we would have a bigger, more expensive signature scheme, but it would have the public key instead of being 2 to the 16 hash values, it's going to be 1 hash value. Okay, so that's pretty useful. But once again, this is one of those places where the simple scheme gets more complicated in order to make it more practical. So key generation, just the same as before. We're going to choose a bunch of random values. We're going to hash them. But now we're going to construct a Merkle tree out of all of our secret values, kind of all these values that 2 to the 16 values that we've hashed. So I'm saying these are sort of public values, right? We've got the secret values, we hash them with the public values, and then we're putting those in the Merkle tree. And we're going to compute the root of the Merkle tree. And from that root, we'll be able to prove membership and position. We actually have to care about the position in the list as well for these signatures. Okay. So this is our public key that we're going to use to do a few signatures. So step 1 of the signature algorithm is we're going to do the same thing we did before. Hash it, break it into 16-bit chunks, use those as indices to look up in an array which values from the private key to insert in the signature. Okay, at this point, we've got the first part of the signature, and that's going to appear in the signature. And then we're going to hash each of these to get our Ys. Okay, so that's step 1. Step 2 is for each of those Ys that we generated, right, which we got by hashing, we're going to generate a Merkle tree path, right? So we have to provide the Ys and then the Merkle tree path. Okay. So this is going to be the second part of the signature. So the full signature is all of these X values, all 16 of them, and then the Merkle tree path for each of the Y values. Okay, so when you receive this, you're going to hash the X value to get the Y value, and then you're going to check the Merkle tree path for each of these. Does that make sense? Okay. So verification also gets a little more complicated. So the first thing we're going to do is, and you can do this a couple different ways, but this is an easy way for you to think of it. We're going to take all of our Merkle tree paths from the second part of the signature. We're going to take all of our X's from the first part of the signature. So we're going to hash those to get a sort of a candidate vector. And then we're just going to verify Merkle tree paths. Are these legit? Are these valid Merkle tree paths? At that point, we know that every X that you gave me, every X in your signature was actually in the private key. We don't yet know where it was in the private key. We have to do that. We still have to check that. But we do at least know, having checked the Merkle tree paths, that it was in the private key. And then the final step is we have to look at each of these Merkle tree paths, but we have to take the message, hash it, break it, split it into chunks, okay, do this part, and then we have to look at each of the Merkle tree paths and verify that it is giving us leaf number T0, leaf number T1, leaf number T2. If you don't do this, you haven't actually verified the signature, so it's kind of interesting to notice. This otherwise would be a signature on some message, but it might not be the signature on this message. Okay, so first of all, does this algorithm make sense? You have questions on the algorithm? All right. Next bit is talking about these extensions. So remember, the other problem we talked about was that a message could have the same value in multiple of these 16-bit chunks, and then it would reduce its security, right, and make it easier to forge. So there were two solutions that people suggested. Gravity Sphinx, which was a post-quantum submission, had one of these. I think actually it was in a paper before that. And this is called pores. So pseudo-random generation onto a random subset. So this is, once again, one of those, what if we did the obvious thing? So in this case, the obvious thing is, instead of taking the hash and generating 16-bit chunks, we're going to take the hash, seed an RNG with it, and then we're going to generate 16-bit chunks from the RNG with rejection sampling. So just every time we generate it, if it's already appeared, then we'll throw it away and try again. And so we're going to generate a non-repeating, like a set with no repetitions. Okay, so having done that, then this is efficient. The thing looks just the same as Horst, except that now we've gotten rid of this problem with weak messages. Okay. The other approach, and this is another one of those what if we just things, this is what's used in Sphinx Plus, is we're just going to use a different tree for every position. So we're going to say, instead of, let me go back here. Okay, so we're randomly generating this. We're going to do this step right here for each chunk, each 16-bit chunk. So we're going to do this for the first 16-bit chunk, and then a new one for the second 16-bit chunk, third 16-bit chunk, etc. We're going to have a whole bunch of Merkle trees. In this case, we would have 16 Merkle trees. And then, of course, you could hash all those together to get the final key. Okay? So that's kind of probably less efficient, a little uglier. It might make the security analysis a little simpler, because you don't have to worry about repetitions from different positions. And so you can kind of look at this. If you choose these parameters that I've chosen, which aren't the parameters that people actually use, they tweak these parameters to get better performance as much as possible. With the horse scheme, a public key is using my parameters, about 2 megabytes, and a signature is 512 bytes. So that's pretty nice. With Horst, pores, and fours, basically the signature is about 8.5 kilobytes. The public key is 1 hash. Okay, so if you were just going to, if you're going to send the public key up front and then only send the signature later, then the Horst signature scheme would be better. But if you're going to send, if you're going to be sending the public key and the signature together, then Horst, pors, and fours are all way better because you're getting a much shorter combined, you're getting 8.5 kilobytes instead of 2 meg. All right. Yes?
Go back a slide.
Yeah.
You said that fours is less efficient than pors.
Right.
Yeah. So why did you choose Sphinx Plus over Gravity Sphinx? What else is different?
Well, Sphinx Plus actually had worked through their parameters, so they were giving us shorter signatures. And we thought that shorter signatures and also a lot of options, a lot of choices. Right? But they had a lot of knobs to tweak. I'll talk about that at the end. But they had a lot of knobs to tweak, and they tried tweaking all of them in different directions to get good performance versus speed trade-offs. So I think, also I would say, hang on, I'll get to you. But also another thing I would say is, I think fours actually makes for a little simpler, maybe a little cleaner security analysis because you don't have to worry about repetitions across different positions. But I mean, you can do the analysis either way. So go ahead. There was somebody.
Does fours, like you would expect that if you have big enough sizes that actually goes to the same security, because I mean you have different trees for each coefficient, but of course the probability of like a repetition is lower, so that would compensate a bit for that.
Yeah, it'll be a little lower, so you probably can do a few. You might be able to do an extra couple signatures with fours and pors at the same parameters.
Does this give asymptotically, is it the same or there's still
No,
like
there's a little difference if you do the calculation, right? So basically, if you're doing 16 components, then every signature is leaking 16 of your secret values if you only have one tree. And if you have 16 trees, then it's leaking 1 from each tree, right? So you're going to be able to do more signatures before you leak, before somebody can forge. So there's some other thing I was going to say. I fell out of my head. So some messy details here. The hash output is A times K. A is sort of the size of the S box or the secret parameter, like 2 to the A is how many secret values we have, either overall or in each tree, depending on whether we're doing Horst or fours. So we can actually, that's 256 in all of my discussion because it's easier to talk about, but you can actually tweak these. It doesn't have to be exactly 256, and so you can tune them to the exact attacks you care about and make a lot of trade-offs in the middle. The main reason we care about these is for stateless hash-based signatures, which I'm going to talk about last. Because otherwise they're just longer and messier, right? They're more complicated and they're longer and they don't do anything you couldn't do. Also, like I said, it's really important for these to use randomized hashes. You don't let an attacker decide offline, choose messages that will give him coverage so he can forge another signature. So, any questions? Okay. Okay, so do I have questions about, I think I've answered the questions about the few time signatures. Anybody else want to? Okay, so then I'm going to talk about hypertrees, trees of trees, of trees of trees, of keys. So the original idea I think goes back to something by Goldreich, but it didn't seem very practical. And Sphinx in 2015 is where this idea, at least I saw this idea really kind of take off and people use it to make a practical scheme. So the big idea is you're going to generate a Merkle tree, and then you're going to use each key in the Merkle tree of keys to sign the root of another Merkle tree. Okay? And so, for all problems in computer science that adding a level of indirection doesn't solve, you try adding some recursion, right? So here's a picture. So in this case, I want to do I have 2 of these Merkle trees, each with 1,000,000 elements, okay? 2 to the 20 elements. And what I want to do is I want to construct a sort of a hypertree with 2 to the 40 leaves, 2 to the 40 signing keys at the end. And so what I'm going to do is I'm going to generate my first 2 to the 20 signing keys up front. That's my key generation. And then, whenever I'm ready to use one of those keys and go down the tree to the next level, then I'm going to generate the full Merkle tree, 2 to the 20 of these keys, construct the Merkle tree, hash it all the way up, get the root, and then sign the root with the first key. And that's when I'm then going to go choose the second key and sign a message with it. So this is a little more complicated. So remember I said about how things are simple and then you pile them on? So this is one of those. So let's look at this with some pictures. So let's think about signing with a 2-level tree, right? So this is a nice picture. So what am I going to do? I'm going to choose a key. Based on that key, so I've chosen sort of a path through this tree, okay? This key and this key. Then what I'm going to do is, having chosen this key, I'm going to go forward and I'm going to say, given this key, which Merkle tree should I compute? Which Merkle tree should I generate? And that's all deterministic. It's all based on the PRF. And I'm going to generate that whole Merkle tree. So I'm going to generate on the fly 2 to the 20 keys. Now, because I'm using a PRF, every time I go down this path and use this key, it'll be the same 2 to the 20 keys. I'm going to generate 2 to the 20 keys, hash them all down to a root, the Merkle tree. Now that I've got that root, I'm going to use this public key that I chose in the first layer of the tree. I'm going to sign that root using just a winner NIST signature. And then I'm going to construct this whole signature. So I've got a tree path to the public key, the first public key, a signature on the root of the second public key, a second public key, a Merkle tree path to the second public key, and I should have the second public key should be here too. So error in the diagram. And then I've got the signature from the second part, the second one-time signing key on the message. So it's a little more complicated. And each of these signatures is pretty big, so you can extend this to an arbitrary number of trees, but it'll be kind of ugly, right? So I'm going to walk through this a little more carefully. For key generation, this is sort of an interesting feature of this. Even though I've got 2 to the 40 one-time keys, for key generation, I'm only going to generate the first 2 to the 20 of them, okay? Key generation, all I do is generate these 2 to the 20 values and this root, and compute the Merkle tree and construct the root. That root is going to be my public key, this scheme. That's all I'm doing up front. So my key generation is pretty fast, okay? 2 to the 20, 2 to the 20 key generations for the winner NIST, and I'm done. And hash it down for a Merkle tree, and I'm done. So that's key generation. Now let's sign something with it. So to sign, I'm going to choose one of these one-time signing keys. Okay, I could choose this. For now, let's assume we're still stateful. So basically, I have 2 20-bit counters. I'm going to use them one at a time, right? So I'm going to keep track of which key I've used here and which key I've used here. So I'm going to use this first key. I'm going to use 2 to the 20 times. Okay. So I'm going to choose this one-time signing key. And now I'm going to generate the second Merkle tree. And this one-time signing key is associated with exactly one Merkle tree, so it always gets the same value. And that's really important because, like I said, if I'm using this in a stateful scheme, I'm going to use this PKJ, I'm going to use 2 to the 20 times. So I'd better always sign exactly the same Merkle tree root with it all 2 to the 20 times. So if I ever got a different root, then I would sign 2 different things with the same one-time signing key and leak my private key. Right? So at this point, I've generated my Merkle tree for my second layer. Now I've made a signature on that using the first key, okay? And now I'm going to choose a one-time signing key from the second Merkle tree, right? Now I'm going to sign the message with that. So we've gone through, it's all sequential. Every step is relatively straightforward, but it's getting to be a moderately complicated scheme now.
How long does it take to 2 to 20 hashes?
So if you were doing this with W equal 4, that would be about 2 to the 30. It would be about 2 to the 30 hash operations to construct the 2 to the 20 keys. So when you see this used for like the stateless hash-based signatures, you use much smaller keys.
Oh.
Right. I'll talk about that a bit. Okay, but there are actually, you can use this for stateful hash-based signatures, and they're defined. And that's you get this, you get a reasonable, and you can do 2 to the 20 keys, 2 to the 20 keys, and just say, whenever I roll to the next key, I have to do another 2 to the 20 work, and that's maybe a few seconds. I mean, 2 to the 30 hashes on a desktop machine or a laptop is not that long. Okay, You might still have smaller pieces. Okay, so at this point, we've got nice 2-level tree signatures. And we can have lots of levels. So we could have 2 to the 30 trees by doing a 2 to the 30 size Merkle tree, or we can have 2 to the 30 trees by doing 3 2 to the 10 Merkle trees. Okay. And of course the signatures will be longer, but it'll be a lot faster to compute up front. And so sort of a question you might ask is, why should I use a multi-level tree, right? So the main answer is, for a single level tree, I have to generate all the keys I'll ever use up front. So if I want 2 to the 4, if I want to be able to do 2 to the 40 signatures for my one-time signature scheme, I have to generate 2 to the 40 one-time signatures. Each one takes 2 to the 10 hashes to compute. So now probably I can't afford to generate my key, or maybe generating my key, I mean, I basically, like, it's like mining a Bitcoin or something, right? Ooh, wait, there's our new blockchain idea. So for a multi-level tree, we only have to generate the keys for the first tree, which means we can actually do this. We can have 2 to the 40 or 2 to the 60 possible keys and still be able to generate a public key and publish the root hash of this and start using it without having generated all these values. So thinking about these multi-level trees, I kind of hop between 3 different representations of them in my head. Okay, 3 different ways of thinking about them. One way is just thinking about it as it's a tree of trees. Okay, it's a hypertree. And that's sort of intuitive when you're looking at it this way, right? We just have multiple trees nested, so each leaf is the root of another tree. Another way you can think of this is that, here I've got 2 to the 20 and 2 to the 20, okay, 2-level tree. I can think of this as a 2-level hypertree, each with 2 to the 20 leaves. I can also think of it as this gigantic virtual tree with 2 to the 40 leaves. But I define it, I get the public key for it without having ever visited any of the final tier of leaves. But I've got 2 to the 40 keys at the end. And at any time, if I decide to, I can visit any of those leaves, right? So you can think of it as a gigantic virtual tree, and I'm only going to touch a few nodes of it, right? I'm only going to touch some subset of the leaves. Also, you can think of this as basically a certificate chain, right? So if you think of this root and this one signature as a stateful hash-based signature, this is basically just a certificate chain, right? Okay, the CA has issued a certificate on this thing, it issues on this thing, on this thing. It's just that the person doing the top-level signing also is just generating those new keys on the fly right when he sends it out. But these are 3 kind of equivalent ways of thinking about it, and different times each one of these is a better way of thinking about this scheme. But it's all of these, right? It's a virtual giant tree, and it's a hypertree, and it's a certificate chain. And I think it also is a floor wax or something. So I showed you before the stateful signature schemes, LMS and XMSS, that are being standardized, and they both have hypertree versions, okay? So these are, the idea here is so you can have a stateful hash-based signature scheme, but you can have 2 to the 40 or 2 to the 60 keys if you're willing to have longer signatures, right? And you don't have to rent time on a supercomputer to generate your keys. So these are some parameters for this, right? So if you have, I think actually this number is wrong. It should be 2 to the 20 total keys in 2 levels, so 2 levels of 2 to the 10. The rest I think are correct. I copied this last night, so if these numbers are wrong, sorry. Just copying them out of a comparison paper. And so you can see, for example, you can have a 6-level tree. Each level is 2 to the 10 keys, and you've got a total of 2 to the 60 trees available. Now these are big signatures, right? They're fast. Computing these signatures is still quite fast, right? But they are pretty big. And you can see another way of getting 2 to the 60 possible signatures where you've got something like 8,600, like 8 kilobytes or something. And so this is sort of cool, right? You can construct you can construct a stateful signature scheme where you don't have to know all the keys up front. You don't have to do this big computation. That's kind of cool. So you have questions on multi-level keys? Okay. So we've done trees of keys and trees of keys. So if I were like a good Dr. Seuss fan, I would come up with some other way to keep it rhyming. But now we're going to talk about stateless hash-based signatures. Okay, and this is sort of the complicated thing that I was trying to build up to throughout the rest of the talk. So we know stateful signatures are hard to get right. We know there's the foot cannon we'd like to avoid. And so the question is, can we do without the state? And I want to point out, even though we're going to do without the state, it's still very much like the stateful schemes we've seen before. Limited number of signatures on a given public key. Same. Signing is releasing secret information. Yeah, just the same. We're going to generate our private key. It's going to be random numbers. Our public key is basically going to be hashes of things. Yeah, okay. The difference is going to be, in a stateful signature scheme, the signer needs basically a counter that always increments for every signature. He needs to be able to keep some state. On a stateless scheme, the signer is going to choose a key to use randomly, right? So inherently, that means he's going to have a lot of keys available more than he uses, right? It seems like it has to be. But now the signer doesn't have to keep track of which keys have been used. That's sort of the cool thing here. That's the powerful thing here. So a big strategy here, right, is we're going to generate a multi-level tree with a huge number of possible signatures, a huge number of possible signing keys at the end. So think of it as this gigantic virtual tree. I want a gigantic virtual tree with a huge number of possible keys at the end. I'm going to limit the signer to only a small number of signatures, small enough that I can compute the probability and show that it's very unlikely he's ever going to reuse a bottom level signing key and sign two different messages with it. And then signing is going to be basically choosing just what I showed you before, choosing a random path through the tree, computing the multi-level signature, and the last key signs the actual message. Everything else just signs something internal. Okay? So from all the pieces we've built up over the last hour and 20 minutes, hour and 30 minutes or something, you can see how this is going to work, right? So the roadmap here, I'm going to show you a kind of a toy version of a hash-based signature that we can kind of show on a diagram and see how it works. And then I'm going to use that to talk a little bit about Sphinx Plus and a little bit about Gravity Sphinx, which are existing hash-based signature, stateless hash-based signature schemes that you can actually use. You can use Sphinx Plus now if you want, or Gravity Sphinx, I think. However, I gotta say, particularly Sphinx Plus, it's quite a complex scheme. The specification is very well written. They did a really nice job of explaining everything, but it is a thick scheme and there's a lot going on. So it's like every piece we've talked about, there's a piece other than Lamport Signatures they're using. So let's build a toy scheme. So we're going to do, let's imagine we build a multi-level tree with 2 to the 64 keys. Okay? We're going to limit ourselves to only 2 to the 16 signatures. So then what's our probability of reusing a key in that case, right? Well, this is a calculation that as cryptographers we do a lot, right? It's just a collision, use birthday paradox thing. So roughly it's going to be about 2 to the minus 33 probability. That's actually the expected number of collisions, but that's pretty close to the probability in this case. So it's about 2 to the minus 33 probability. So about 1 in 8 billion that we're going to reuse a key. Now, let's suppose for the sake of making this description easy, that is an acceptably low probability of disaster for us. Then we could do a scheme like this. If you found that this was not acceptable, given a maximum number of signatures and an acceptable collision probability, you can figure out how many keys. It's like a simple formula. You can figure out how many keys you need in this giant virtual tree in order to be able to have an acceptably low probability. So maybe for a real system, maybe you'd want this probability to be 2 to the minus 60 or something, and then you just make there be more keys, right? Add 2 to the, I don't know, maybe just 2 to the 30 more keys or something. Or maybe 2 to the 90 keys instead of 2 to the 60. Right? So for key generation, we're just gonna, like I said, just gonna generate 2 to the 16 one-time signing keys, winner nits keys, drive them up, derive the root public key, and the root public key is the thing we're gonna publish. That's our public key for our scheme. And we're gonna define a PRF seed that will be used to define all the lower trees. So it's kind of weird. Once I choose my PRF seed or my key, then basically I've already committed to every value of this, every leaf in this giant virtual tree, even though I don't know any of them yet. But it's all defined by that PRF. And once I've chosen the PRF seed, I have no choice over what happens after that for any of those keys. And if I did, then it would be really bad, actually. So each of these trees has 2 to the 16 trees. The first 3 trees, each one's going to have a different Merkle tree below it, just like I talked about previously, but now we've got more levels. And each leaf in those first 3 trees will only sign one thing ever, and that is the root of the tree below it. Okay. And then the last tree is actually going to sign a message. So we have 2 to the 64 total keys in the bottom level, but we're only going to use 2 to the 16. So if you think of this as this giant virtual tree with 2 to the 64 leaves, we're going to randomly visit a leaf each time, and we're only going to visit 2 to the 16 of them. And then we're going to say we have an acceptably low probability that we'll visit the same leaf twice. Okay. So for signing, just like we said before, right, we're going to choose a path through the tree. For all these intermediate layers, we're going to look at the key, rederive the key below it, recompute that whole, all those 2 to the 16 keys, rederive the root, the Merkle tree root, sign it, and then we're going to go down to the next layer and do the same thing with the next key. Do that 3 times. We'll do the same thing for the last tree, and then we'll have one more signing key. And this one-time signing key we will use to sign the message. Right? Does this make sense? It's just building on all the stuff we've done before. And so you can see this message, the full signature is going to be a key path, a signature on a root, key path, signature on root, key path, signature on root, key path, and now a signature on the message. Okay? So this is, we can do this. We already know how to sign this and how to verify this. It's just the hypertree stuff we just did. For verifying the signature, actually that's really easy. We verify each Merkle path, get the next one-time signing key, use it to verify the next Merkle tree root, and just keep going. And then on the final thing, we verify the signature on the message. So given just the root public key, the root of that top Merkle tree, given just that, we can verify any signature we want to do on this. And this is, I keep harping on this because it's a really important property of this. Even though we're randomly choosing a key each time, we're randomly choosing a path each time, these inner keys can never ever sign, they can never fail us. They can never sign 2 different messages, okay? Each of these keys is only allowed to sign the one thing that it's defined to sign. And so the result is we never have to worry about internal collisions causing a repetition, like signing 2 different messages on any of these inner layers. Only on the bottom layer do we have to worry about this, okay? And so then the bottom layer we could screw up. We could sign 2 messages with the same key. And so we just have to limit the number of signatures relative to the total number of keys to keep that acceptably low. So in my toy example, it's 2 to the minus 33. For a real world system, you'd want that to be a little lower, but gives you the idea. Okay, so how big are these signatures? Now I haven't tried to optimize this. I haven't tried to do anything super clever here. And there are a lot of optimization knobs that you could twist. But these schemes, just as I've described, using like 256 element chains and winter knits, which you could do with this reasonably efficiently. So this would give you about 6 kilobyte signatures. And so it's kind of interesting to think, so you can get, for kind of comparable performance, you might get like a 2 kilobyte signature with a stateful scheme or a 6 kilobyte signature with a stateless scheme, right? However, there are a lot of knobs to twist to get better performance, and I'll show you that in a second. So, all right, I guess I'll stop. Do we have questions about stateful or stateless hash-based signatures? Go ahead.
Yeah, okay, just so can you go back to the previous slide?
Yes.
Just so I understand what's going on. So when I sign, I generate all of the path of the trees, trees I select. I generate the hashes at the leaf nodes of each of those trees. Hash, and then give the path.
Right.
So if those are the paths, that's 2 to the 16, is it? Keeps at the bottom of each one?
Yeah, so it's 2 to the 16, and then, I'm sorry, what was
So
your?
that's 2 to 16.
Right.
Each one of those takes 2 to the 10. Yeah, so it's 2 to the 26 for
Yeah.
each tree.
Right,
And then I've got 1, 2, 3, 4 trees, so that's 4 times 2 to the 26.
right, so like, yeah, like 2 to the 30 or so.
You put it like
Right.
that.
There's probably an order of magnitude that could
Yeah.
slide in there for things we're missing, but yeah, that's approximately right. That's basically right. So you could do this. You could actually, this isn't something where you start the thing signing and go make yourself a cup of coffee and, come back and the room's warmer. I mean, this is, so, okay, so that's the basic scheme. Oh, yeah, go ahead.
So just understand, so if you want to sign, you have this message, and then you choose a route through the tree.
You choose an entire path through the tree.
How do you choose it? Like, is it based
So,
on the message? And then
In principle, you could choose it randomly, right? Although the stateful schemes all basically do it, sort of like the stateful DSA, stateful ECDSA. So they'll take a secret value that is part of your private key plus the hash of the message and hash those together to generate something. And I think so. Sphinx Plus also has a thing where they actually can accept additional randomness, but they don't rely on it. So you can think of it as choosing a random path of the tree, but really you'd like to do this so that you don't need an RNG to compute these.
So they make use of randomness to make sure that which is not the message. Like they need additional randomness to make sure that it's a random path to the tree.
Right. So you're going to choose. Our goal is to choose a random path through the tree. However, because there's no problem if you sign the same message with the same key. There's only a problem if you sign different messages with the same key. It's actually fine to take your message and feed it into a PRF and use that as your random seed that you use to choose your path. And because then if I give you the same message twice, you'll just get the same.
So in effect, you could deterministic signatures.
Yeah. Now, you could define them so that they use a random number generator. There wouldn't be anything wrong with that. It's just that in practice, it's cleaner to design them so that you just use the PRF. So go ahead.
Can you go a few slides back?
Yes.
The one before? Yes, here.
Oh.
Yeah, that one.
Yeah.
So you're using a PRF to deterministically generate such that there's no two different messages that are signed.
Well,
Okay.
I can't use a PRF to generate this message. This message comes from outside. But all of these values are internal. So yes, I use a PRF to generate all those.
Yeah. From an implementation point of view, if I manage to introduce a fault anywhere in those computations, does that mean security is gone?
I know that there are fault attacks on these schemes that people have talked about. I would have to look at it to see. I'm not sure what all you do. I mean, one thing you could always do is one fairly good defense against a fault attack with a scheme like this would be to sign twice, right? And okay, they were slow, so now we'll make it slower. But if you sign twice and verify that they're identical signatures because it's deterministic, you'd be fine, right? But I believe that somebody has talked about attacks on fault attacks on these schemes, and basically, yeah, if you could cause me to generate a different, 1 bit different in one of these keys, so I generated a different root signing with this one time than the other, then yes, you would now know how to forge signatures off of this thing. And from knowing how to forge signatures off of one-time key in one of these trees, you could just forge signatures from the stateless scheme forever, right? So yeah, it would be very catastrophic if you did this. Okay, other questions? All right. So I'll talk about Sphinx Plus, and this is sort of, remember my story about hash functions where you start with hash-based signatures. You start with simple ideas, and you just come up with more ideas and pile them on until you get this really complex scheme. So that's the hash-based schemes. Sphinx and Sphinx Plus and Gravity Sphinx all have that property. There's a lot going on. So it's kind of a complicated spec. It's well written, but there's a lot to it. There are a lot of options, but everything in there except for I think the tweakable hash functions that they use for for their security proof. I think everything in there we've covered. So all the hash-based signature related things we've covered today. So you should actually be able to read the spec after this. So The reason I said before, one reason why people are looking at hash-based signatures again after their beautiful birth in the 70s and their glory in the disco era was that people realized that quantum computers could be showing up sometime soon, and we would like signature algorithms that will stay secure even if somebody has a quantum computer. So when we put up our requirement for the post-quantum crypto competition, for secure signatures, we have these two requirements. One is that it has to be stateless, right? One is that it has to be able to sign at least 2 to the 64 things securely. So it's interesting because the exact choice of 2 to the 64 for I think all of the other signature schemes is completely like no problem, doesn't cause any heartburn. For the stateful hash-based signature schemes, this is like huge heartburn, right? So if we said 2 to the 32 instead, the stateless hash-based signature schemes would be much shorter, right? So 2 to the 32 would be too little, but you see that how many signatures you can do matters a lot for the size of these signatures. You can see that with our toy example, right? If I wanted to be able to do 2 to the 32 signatures in our toy example, I'd need probably another 4 or 5 layers of tree to get away with it. So the kind of point of this was we wanted the new signatures we got for post-quantum to be sort of drop-in replacements. We wanted to be able to say, you have an RSA signature, you need something post-quantum, and so we want you to drop in something that just works the same way, right? So all of your protocols, your designs should not have to be re-engineered to think about this new set of requirements for stateful signatures or doing some sort of CRL-like check every time to make sure it hasn't been reused or something. So because of that, that ruled out the stateful stuff. Okay. Now we're still working on standardizing the stateful stuff for limited use, but that's a different effort, right? And it's sort of striking. One of the comments at the post-quantum workshop Andreas Schulzing made was, he's one of the Sphinx designers, is that basically saying, if you could relax this requirement down to 2 to the 50, we could give you much nicer signatures. So Sphinx was published, I believe, 2015, and it kind of showed that you could make a full stateless hash-based signature scheme and it'd be practical, right? There was an earlier idea from Goldreich that showed that you could do this in principle, but it wasn't, this is actually where you get a practical scheme that you could use, okay? And then basically there were 3 stateless hash-based signatures proposed for NIST post-quantum competition. One of them is Picnic. Everything I've told you about hash-based signatures for today does not apply at all to Picnic. It's a completely different design, unrelated. It's like comparing, I don't know, like bears and lizards or something. They're completely different parts of the tree. So Picnic is based on MPC in the head and zero knowledge proofs. It doesn't have anything to do with this stuff. The two that have to do with what we've been talking about are Gravity Sphinx and Sphinx Plus. Okay. So I'm going to talk mainly about Sphinx Plus because Sphinx Plus wound up as the round 2, the one of these things that made it to round 2. Gravity Sphinx didn't. The basic idea here, though, is we have a top-level Merkle tree. We're doing the winner NIST signatures, but we're adding one extra thing that we didn't have, and then we're adding one extra thing we didn't have in the previous things, which is we're going to use these few time signatures at the end. Okay. So instead of having all winner NIST one-time signatures, we have all winner NIST one-time signatures in the middle, right, where we can guarantee that will only be used for a single thing. And then at the end, for the last node, the last level of leaves, we have few time signatures that maybe we maybe can sign 4 or 5 times with them without a disaster. Okay. Now, why would we do that? So the basic idea is, if you think about it, pairwise collisions, it's for the same number of iterations, the expected number of pairwise collisions is much higher than the number of 3 collisions, 5 collisions, 20 collisions, etc. Right? And so what happens is you can get away with using a smaller, if you think of this giant super virtual tree with a zillion, with 2 to the 60 or 2 to the 80 or whatever keys, you can use a smaller virtual tree if you're using few time signatures that can survive being used 8 or 10 times or something. Okay, and so you're going to do the same calculation, right? You're just going to compute the expected number of K collisions, and if it's like 8, then the numbers look nicer. Okay, so as an example of this, let's suppose we've got a scheme that it can survive 3 signs. You can sign 3 times with it, but if you sign a 4th time, then it's a disaster. Okay, and let's imagine we do this on our toy scheme, right? So we're going to take our same toy scheme that I told you about, 2 to the 64 leaves, but now the leaves are all going to be these few time signatures that can survive 3 signatures but not 4. And in that case, for the same roughly the same probability of disaster, instead of allowing 2 to the 16 signatures, you could allow 2 to the 41. Okay. Now, this assumes I did this calculation right, which I did like 2 hours ago, but I'm pretty sure this is right. So, all right, so this is just computing the expected number of K collisions. Okay. So you're just really saying how many K tuples were there, how many triples were there, how many quadruples were there, and then what's the probability that any one quadruple all hit the same place. Okay, and so the idea is this lets you have many more signatures in the same hypertree. Okay. And that's a huge advantage. Sphinx did that, and then Sphinx Plus and Gravity Sphinx also did the same thing. So Gravity Sphinx did pores instead of pores, so instead of Horst, so they did the pseudo-random generation to make sure they didn't repeat a 16-bit chunk. And they did this thing called octopus authentication. And what that means, I didn't discuss that because it didn't seem terribly relevant, but if you think about this, about the Horst signatures, where I have a Merkle tree and I'm authenticating many different nodes in the Merkle tree, like 16 nodes, often there will be some overlap between some of the trees, some of the tree paths. So that means you can shorten the signature a little bit. You can omit repeated nodes, and that makes the signature a little shorter. And it's probabilistically, so it might be, the worst case is that it's the same length as before, but sometimes you can shorten the signature. Okay. They did a couple other things, like they had the first tree was big. The first tree was 2 to the 15 nodes, or 2 to the 15 hashes, and they would pre-compute that and cache it. Right, and then they would just assume you could hold that Merkle tree in memory, and then you could do faster signatures as a result. And so they had some optimizations. And then Sphinx, going to Sphinx Plus, they fixed many of the same problems. Did a few changes, multi-target resistance. They did fors, the thing where you have a different tree for each component of the hash, so every 16-bit chunk gets its own Merkle tree in the few time signature. So they did that instead of Horst. They added verifiable index selections, so basically you as a receiver can verify that the correct path through the tree was chosen based on the message, even though you don't know the PRF key. They added a feature for optional randomness, and they had a lot of options. So, without talking about a whole lot of detail, I want to point out there are a huge number of these options, and we've talked about all these. So if you want to look at this at their spec, the winner nits parameter, the height of the multi-level tree, how many levels in each tree, so how many subtrees, how many trees of secret values, how many leaves in each of those trees. Those are all parameters. And so an interesting feature here is that there's this huge set of parameters, huge space of parameters. And so then you kind of have to try a whole bunch of different ones to see which ones give you better performance. And so they chose a different parameter set for basically 6 different parameter sets that they proposed. And I wanted to show this because it shows the trade-offs in size versus speed. Okay? And so they actually name these something Sphinx plus 128S and Sphinx plus 128F. Right, which is for small and fast, or you could also, I'm stealing this from somebody, you could also equivalently say slow and fat because it's the same, it's just each side of the trade-off. So the small signatures are very slow, the fast signatures are bigger, right? As you can see, by making it slower, you can make the signature about half the size, okay? And also it's kind of interesting to say, well, this is kind of practical, even 16 kilobyte signatures, I mean, there are a lot of applications that wouldn't work, but you can think of applications where they work. So this isn't totally unworkable. And these are performance numbers for this. and I wanted to show you this is our own internal stuff, so you could also get super competent, maybe more accurate. This is just us looking at the reference implementation. Sort of the driving thing here is look at the difference between the fast and the small in terms of the work, right? So you can see it's like maybe like a factor, 14 or 15 more work in order to make the signature half the size. So they're putting a lot more computation in. They're pretty far down the trade-off curve to get down to that, right? And I think for comparable, you probably get like a 2 kilobyte signature with like LMS or XMSS to do comparable security. So if questions on the stateless schemes? All right, we're good? Kind of like hammered you all with too many details now. So let's wrap up, and this is pretty short. So if you don't remember all the details, which you won't unless you go look at these things, you can remember all hash-based schemes, all of these schemes have these properties, right? There's always a limit to how many times you can sign. Signing is always revealing secret information, which is why there's a limit. Verifying is almost always just taking pieces of the signature, hashing them, and then comparing them to the private key, maybe chasing down a Merkle tree path or something. And all the underlying ideas are simple, but then the full schemes, you pile everything on to get it to be practical. And so we've kind of covered the 1970s and then later. So I really wanted to bring like a soundtrack, like some ABBA songs or something. But the stuff later is actually quite surprising, quite cool, right? And it would have been easy to think in 1980, okay, this is mined out, there's no more cool stuff here. But there is. And so one thing that I have, and this is a general question, I don't have a good solution, I don't have a good answer for, maybe you guys have an answer, is we can build signature schemes from just symmetric crypto, just hash functions. And even though they have some limits, like there's a limit to how many signatures you can do, they're practical, you can use them. If you set the maximum number of signatures to something small, like 2 to the 15 or 2 to the 20, they'll be pretty reasonable sizes, right? I mean, they'll still be big, but they won't be unworkable. So we can actually get signatures from nothing but a hash function. We have no way of doing that with key agreement schemes. I don't know, how many of you know what a Merkle puzzle is? Merkle's puzzles? You never saw that? Okay, a few of you saw it. Merkle's puzzles are really simple, right? The idea is I'm going to encrypt a bunch of plain text. I'm going to send you a plain, like an encrypted text. I'm going to encrypt a bunch of plain texts with, I'm going to encrypt one key with a bunch of different random keys that are all weak. Let's say they're 30-bit keys. I'm going to send them all to you. I'm going to send 2 to the 30 of them to you. You'll choose one and break that, and do a 2 to the 30 brute force search and break that one and get a key out. And then you'll encrypt a message back to me with that key. Okay. The idea is I'm doing 2 to the 30 work, you're doing 2 to the 30 work, and an attacker in the middle is doing, in that case, would be doing 2 to the 60 work. Because you'd have to try every one of them, or at least half of them. Okay. So I should have written a slide for this. I thought everybody would know it. So the cool thing with Merkle puzzles is it gives you a key agreement where it seems like it should be good. It's symmetric crypto, and it's based on this, and it gives you an advantage. But the advantage is order of n squared. Okay, and that's never good enough. It just never works out that gives you a useful key agreement scheme. If it were order of n cubed, you could actually do it. It would actually be practical. So I keep wondering, as a philosophical question, why is it that the world works in such a way that you can do signatures with symmetric crypto, but you can't do key agreement with symmetric crypto, get it to be useful? So it feels like, okay, there's some alternate universe where pi starts with a 4 in the first digit that you can do key agreement with symmetric crypto but not do hash-based signatures. I don't know, but it's kind of cool. It's an interesting question in my mind. So kind of thinking about stateful hash-based signatures, they're practical, they're fast, they're quantum secure, they're great as long as you can convince yourself that you won't reuse the state. You won't reuse a key. Stateless signatures are a lot bigger and slower, but they are kind of arguably practical. Verification is still usually pretty fast. And it does away with the foot cannon at the cost of these bigger, slower signatures. So if you think of stateful hash-based signatures and you say, I'd like to find some good crypto solution to the reuse of state problem, stateless hash-based signatures are basically one attempt. They're one way of solving that problem by saying, well, we'll just randomize the choice. And it's kind of interesting to look at the difference. So the shortest signature you can get, which is fairly slow to compute with Sphinx Plus, is over 8,000 bytes. And comparable signature strength with XMSS or LMS is like 2,500 bytes or something. So it's kind of, you are paying a price for the stateless property, okay? But on the other hand, you're getting some benefit from that because then you've got, you don't have to worry about reusing a key. And the last thing I'll say is I think that there's actually still interesting work to do here. I don't think this area is mined out. I think, the Sphinx is 2015. So I think there's cool stuff you could still do here. And that's it. So if you have any questions, I'll take them. Thanks a lot.